Great. Now we'll look at two more theorems, very powerful theorems. First one is a Fermat's theorem. Okay, so Fermat's theorem basically says for any two positive natural numbers n and p, if they are co-prime to each other, then remainder obtained when n is raised to the Euler's totient of p. Now this is Euler's number or Euler's totient of p is 1. Okay, the remainder is 1, as simple as that. What is Euler's totient? If you remember our factors wala class, we had discussed numbers which are co-prime to n less than n. That value is called the Euler's totient. For example, if I have a number 12 and I ask you how many numbers lower than 12 are co-prime to 12. How did we find that? 12 was equal to 2 square into 3. So such number, which we denoted by 5, will be equal to 12 into 1 minus 1 by 2 into 1 minus 1 by 3. Okay, so 12 into half into 2 by 3 or 12 by 3, which is 4. This number is called the Euler's totient. Okay, this number is called the Euler's totient. Okay, so understand the composition, very important. N and P should be co-prime to each other. First part. Remaining we can solve, but this N and P have to be co-prime to each other. Okay. N and P, they're co-prime to each other. Okay. Then, and this power is the Euler's totient of P, then the remainder is 1. Okay. As simple as that. There's a modification of this also. And the modification says this n can be power of the totient and a multiple, same that we had in my remainder theorem also. So it can be a multiple also, that's not a problem, as long as it's a multiple, as long as the power is the totient, Euler's totient of P, and even if it's a multiple, does not matter, still the remainder will be 1. Okay, you'll understand this better when we do couple of questions. And this can give you the answer instantly, but only in certain cases. Okay, for example, let's look at this. 77 to the power 8 is divided by 24. So first, what will you check to see can I apply Fermat's theorem or not? And Fermat's theorem, we sometimes also call it Euler's theorem because we are basically using the Euler's totient. Okay, so first thing is 77 and 24 have to be co-prime. That is the first fundamental rule to apply Fermat's. Rest everything we can manage if they are co-prime. So 77 is 7 into 11 and 24 is 2 cube into 3. There is nothing common, so I can apply. Then what is my Euler's totient of 24? 24 into 1 minus 1 by 2 into 1 minus 1 by 3, which is 24 into half into 2 by 3, which is 8. That is exactly what is given in the power. So this is copy made for Fermat's theorem. You straight away can apply this. Okay, so this, now just remember what was my this n to the power Euler's totient of P. So 77 to the power Euler's totient of P divided by P, right? And P and this should be co-prime. All conditions satisfied, then in that case straight away your remainder is 1. So the answer is 1. You don't have to do anything if it falls in the format. Your remainder is 1, right? As simple as that, and that is your answer. Okay, let's look at one more. Very similar to previous question. If you see, it was 77 to the power 8 divided by 24. Here it is 77 to the power 100 divided by 24. Okay, and why I have taken the same example to show you that the fundamental condition that n Euler's totient of P upon P, n and P should be co-prime. That is one condition that you can't bypass. So if you have to apply Fermat, that must hold true, and that is still holding true. But now you can see that n raised to the power is not Euler's totient. the Euler's totient of 24 is 8, but I have 100 here, which is fine. I can use modified Fermat's theorem. So what I will do is I will write it as 77 to the power 12 into 8 into 77 to the power 4. It adds to 100, right? 12 into 8 is 96. 96 plus 4 is 100 upon 24. Okay, I can write it like this. And this part, modified Fermat's theorem, can be applied. Okay, because what was the modification? N raised to the power m into Euler's totient of P upon P is also fine. This will also give remainder of 1. And that is exactly what is happening here. 28, Euler's totient of 24 is 8. So this will give me remainder of 1. Okay. Now what remains is 77 to the power 4 upon 24. Okay. So this is the part that remains. And then how do I solve for this part? So this part, there are a lot of ways in which I can do this, but let's do this using the simple method. What I'll do is 77, if you divide by 24, you get remainder of 5, right? And if you remember, I had told you that dividend at any point of time can be replaced by the remainder. So basically this is equivalent to 5 to the power 4 upon 25. Upon 24. The remainder will be same in this case. Now 5 to the power 4 can be written as 25 into 25 upon 24. Okay, so 25 divided by 24 will give you remainder of 1. 25 divided by 24 will again give you 1. 1 into 1 will give you 1. So the remainder of this part is 1. The remainder of this part also is 1. Net, the remainder is 1. So the answer is same. Answer is 1. Okay, so when you don't want to apply any formula or any theorem, you can just do it manually, and this will definitely keep reducing the number. If 77 to the power 4 became 5 to the power 4, and then you reduce it further and reduce it to a level where you can do it manually. So that is something that will always work, and that can be done. Okay, so this was Fermat's theorem. Fermat's theorem, remember, can be applied only when the number that is getting divided is co-prime to the divisor. That is the rule that you have to apply. Rest everything can be managed, but this condition must hold true. Okay, fine. Let's look at the last theorem, which is Wilson's theorem. And Wilson's theorem applies in a very special case where your dividend is a factorial. We have so far raised dividend to powers, and when you have raised dividend to powers, you can use cyclicity, you can use remainder theorem, you can use Fermat's theorem. But when your dividend is a factorial, which is, so your numbers are getting multiplied, then normally nothing else will work. And that is where your Wilson's theorem works very beautifully. Okay, so Wilson's theorem says that when p minus 1 factorial is divided by p, okay, p minus 1 factorial, remember, p minus 1 factorial is divided by p, where p is a prime number. It's important, p must be a prime number. Then it gives a remainder of p minus 1 or minus 1. Your remainder is p minus 1 or minus 1. Okay, for example, when 4 factorial is divided by 5. So this is p minus 1 is divided by p, 5 is prime number, we get 4 as the remainder. Or we can even say minus 1 is the remainder. Similarly, when 6 factorial is divided by 7, we get 6 as the remainder. 10 factorial is divided by 11, we get 10 as the remainder. Okay, so important, your p should be a prime number, your divisor is a prime number, and your dividend is p minus 1 factorial. Okay, then there is a extension or modification of Wilson's theorem, is when p minus 2 factorial is divided by p, then the remainder is 1. Okay, so here the remainder is minus 1 and here the remainder is 1. For example, when 225 factorial is divided by 227, 227 is a prime number. Okay, so 225 factorial is divided by 227, we get a remainder of 1. Okay, so very powerful rule, and we'll do a couple of questions explaining this. And this is the only theorem that can be used to solve factorial questions. Okay, otherwise you can do it normally, but if you have to apply a theorem, then Wilson's theorem is the only theorem that comes in handy. Okay, so let's look at this question. What is the remainder when 15 factorial is divided by 19? Now, using Wilson's theorem, I know that 18 factorial when divided by 19 will give me remainder of -1. Using extension of Wilson's theorem, I also know that 17 factorial divided by 19 will give me remainder of 1, right? But this is 15 factorial. I don't know for 15 factorial, right? So what do we do here? So this is where the method becomes very beautiful, that actually it can be any factorial. As long as it is smaller than the number, I can do manipulation, and that modification of Wilson's theorem, I can modify it further. The only condition that must be met is that my divisor must be a prime number and my dividend must be factorial of a number smaller than the divisor. So 19, you must have smaller than 19, which is the case. Okay. So let's look at this here. 17 factorial. This I know. Let's start from here. 17 factorial can be written as 17 into 16 into 15 factorial divided by 19. This will give me remainder of 1, right? Because 17 factorial upon 19, I know from modified Wilson's theorem, gives me remainder of 1. Let's divide these separately. 17 by 19, 16 by 19, and 15 by 19 anyways there. So 17 divided by 19 will give me remainder of 17 or -2. 16 divided by 19 will give me remainder of 16 or -3. And then 15 factorial divided by 19. Net, the product of these remainders is going to be 1. Okay, so these are the this is the remainder. This I already know. Now -3 into -2 into -3 is 6. So 6 into 15 factorial upon 19 is equal to remainder of 1. Fine so far? Now what do we do here? Now if you think I need to remove this 6 from the left side, right? Then on the left side you will get what you want, 15 divided by 19 remainder. So let's do one thing. On the right hand side, this remainder which is equal to 1, I can also say this is remainder of -18. 1 and -18 is same, right? Because your divisor is 19. So I'm converting a positive remainder to a negative remainder. So 6 into 15 factorial by 19 gives me a remainder of -18. Why I have done -18? Because this 6 and -18 can be cancelled and I'll have -3. So 15 factorial divided by 19 will give me a remainder of -3. -3 means what? -3 plus 19, it means my remainder is going to be 16. So 16 is your answer for this question. Okay, so this is how your Wilson's theorem is used, and as long as your divisor is prime and your dividend is a factorial of a number lower than the divisor, I can adjust. If it is 1 lower, your formula applies directly. If it is 2 lower, your modified Wilson's theorem applies directly. If it is further lower, no problem, we can still solve it using this. Okay, so watch this solution carefully and understand how this is being applied. We'll do one more question on this. So what is the remainder when 23 factorial is divided by 47? 23 factorial square. Now you can see that again we are very far, but this, because there is a factorial, this has to use Wilson's theorem. Because the divisor is a prime number, this has to use Wilson's theorem. Okay, but from Wilson's theorem, you know that 46 factorial upon 47 will give you a remainder of 1, right? No, not 1. It will give you a remainder of -1 or a remainder of 46. This is what we know. Okay, so 46 factorial if I start opening it, it will be 46 into 45 into 44 into 43 up to 24 into 23 factorial upon 47. It gives me remainder of, right, this is what I have. Now this part that I have, 46, 45, 44, 43 up to 24, you can see that this will basically contain 23 terms, right? This has 23 terms, out of which 12 terms will be even and 11 terms will be odd, right? Okay, so let's do one thing. What if I divide this 46 by 47? What remainder do I get? 46? Or I can say minus 1. So this one will give me a remainder of minus 1. Next one, 45, will give me remainder of minus 2. 44 will give me remainder of minus 3. And this will go till 24, which will give me remainder of minus into 23 factorial divided by, this is what I have. This gives me remainder of, fine till here? Okay. Now you can see that here I have a total of 23 terms, right? 23 terms. So net the minus sign will remain. So you'll get minus, and this, if you remove the minus, you can see that here 1 into 2 into 3 into 4 into up to 23. That means this is also 23 factorial. So minus 23 factorial into 23 factorial upon 47 gives you remainder of minus 1. So in fact, minus and minus will get cancelled. Okay, 23 factorial whole square upon 47 will give you a remainder of 1. That's all. So your answer is going to be remainder 1. That is the answer for this question. So this again is a beautiful application of Wilson's theorem, how this question can be solved. Okay, end of this class. We have discussed remainder theorem, we have discussed cyclicity, we have looked at Fermat's theorem, we had looked at Wilson's theorem, Euler's totient, and so much more. Okay, so with this we also conclude our numbers class. Please go through all that we have discussed. We have solved fair number of questions, but there can obviously be more questions that you can solve, and get confidence here because the variety of questions in numbers is unlimited. But there's nothing that you should not be able to solve now, given that all the concepts that we have touched upon. Okay, so thank you so much, and then see you in the next class. This is Nishant signing off. Bye bye, take care.